Let's start with a picture. Imagine your brain as this huge, sprawling city. You've got billions of neurons, and they're like little messengers just zipping around constantly, carrying signals that control literally everything you think, feel, and do. It's the most complex, most efficient communication network we know of anywhere. But what happens when that network starts to fail? You know, when the messages get lost, when the lines of communication start to go down, and whole neighborhoods of that city slowly fall silent? That's the huge question we're going to tackle as we dive into the world of neurodegenerative disease. And there's a name for this breakdown: neurodegeneration. And it's not like flipping a switch. It's this slow, progressive failure of that incredible communication network that we all depend on every single second of the day. So the definition really gets to the heart of it. These are diseases all about the progressive loss of our neurons, those brain messengers. First, they stop working right. Then their actual structure breaks down, and eventually they die. We're not talking about a temporary glitch here. This is a permanent loss of the brain's actual hardware. And this right here just lays it out so clearly. On one side, you have that healthy neuron just firing off signals, doing its job perfectly. But on the other side, you see the degenerating one. It just can't do its job anymore. The message doesn't get through, that connection is lost, and the neuron itself just fades away. To see how devastating this really is, let's look at a specific example. Okay, let's make this real with a case study: Parkinson's disease. Now, a lot of us immediately think of tremors, but at its core, it's a neurodegenerative disease that zeroes in on the brain's ability to control movement. So what's actually happening under the hood? Well, Parkinson's is caused by the death of some very specific neurons. They live in a part of the brain called the substantia nigra, and their whole job is to produce dopamine, a super important chemical messenger that helps regulate our motor signals. So when these dopamine factories start shutting down, the brain's control over movement begins to fall apart. And this loss of dopamine is what leads to those classic motor symptoms. You get bradykinesia, which is basically just a slowness of movement. There's rigidity, which doctors sometimes describe as feeling like a cogwheel or a lead pipe when they try to move a patient's limb. And of course, the tremor, which you notice most when someone is at rest. In fact, to get a clinical diagnosis, a doctor is usually looking for at least 2 of these first 3 symptoms. Now, this phrase here is such a classic description. The tremor is often called a pill-rolling tremor. And it's because it literally looks like the person is rolling a little pill between their thumb and index finger. It's an incredibly vivid image, and it's a key sign that often vanishes when someone's trying to do something, but it comes right back as soon as their hand is resting. And we're not talking about some super rare condition here. The impact is huge. Around 1% of all people over the age of 60 have Parkinson's disease. Okay, so now let's shift gears and look at a different part of the brain's city and a completely different kind of neurodegeneration. So if Parkinson's wages its war on the brain's movement control center, Alzheimer's disease attacks something else entirely: our memory and our ability to think. It's the #1 cause of dementia, and its method of attack is different, but just as destructive. You see, Alzheimer's is a kind of 2-pronged attack. First, you get these sticky proteins called amyloid plaques that build up in the spaces between the neurons, basically gumming up the works. And then another protein called tau forms these twisted tangles inside the neurons, choking them from within. So it's this brutal assault from both the outside and the inside at the same time. And the wild thing is, this whole destructive process, it's not random at all. It actually follows a pretty predictable path. The disease usually starts in the brain's limbic system, which is absolutely crucial for forming memories. And from there, it just spreads out in a stereotypical pattern. And that's why the symptoms also tend to progress in a predictable way. At first, the symptoms can be really subtle. I might start with just having trouble remembering recent events. That's the classic memory impairment. But as the disease spreads, it starts to affect language, the ability to organize thoughts, and even impulse control. And honestly, one of the biggest challenges is that these early signs can look a lot like normal aging, which means a diagnosis can be delayed for a long, long time. So we've looked at 2 very different diseases, attacking different parts of the brain in completely different ways. And this brings us to the biggest question in this whole field: what makes finding a cure so incredibly difficult? This table just lays it all out, crystal clear. The symptoms of any neurodegenerative disease depend completely on where the neurons are dying. For Parkinson's, it's the substantia nigra, so you get movement problems. For Alzheimer's, it starts in the limbic system, so you get memory loss. Each disease has a different location, a different problem protein, like alpha-synuclein or amyloid and tau, and a totally different outcome. This makes a one-size-fits-all cure pretty much impossible.
And because we can't actually stop the cells from dying, most of the treatments we have today are really just managing the symptoms. For example, the best drug for Parkinson's is L-DOPA, and it works by basically replacing the dopamine that's been lost. But it's a temporary fix. The brain's dopamine factories are still shutting down, which means patients need more and more of the drug until eventually the side effects can get worse than the benefits. We're just patching the holes. We're not fixing the leak.
And this is the stark reality we're all facing. It's a quote directly from our source material, and it captures this modern paradox. Our success in medicine means we're all living longer than ever before. But that very success has created a whole new challenge: age-related brain diseases. The longer we live, the greater the chance that our brain's incredible network starts to fail. Which leaves us with this final, massive question. We've gotten really good at preserving the body, but the next great frontier for medicine, and for all of us really, is figuring out how to preserve the brain. As we keep extending our lives, what is the secret to protecting that intricate, incredible network that actually makes us who we are?